In today's video, I'll show the build of a completely overhauled standalone matrix display. I'll show some of the major features, including how, with the click of a button, the matrix can also become a full WLED display with hundreds of additional effects and features. I'll cover the build details, wiring diagrams, the required and optional parts, a bit of the firmware and settings, and, while not required, how you can optionally use a new API to integrate the matrix with Home Assistant. Hi, and welcome to Resin Chem Tech. About 5 years ago, I did a poorly produced video on my first matrix build that eventually became a clock with some scoreboard and some additional features. That original build, however, required Home Assistant and an MQTT broker to be able to control and use the matrix. Now, this required a lot of Home Assistant YAML, nearly 2,000 lines, and I found that a lot of folks struggled to migrate this into their own Home Assistant. And of course, those without Home Assistant were simply left out in the cold. This new version is about 35% smaller, but still has the same number of LEDs. It's an upgraded version that uses an ESP32 instead of an ESP8266, and is completely controllable and configurable through its own web application. Of course, you can still integrate it into Home Assistant through a new API that's available for this newer version. But of course, Home Assistant integration is certainly not required, and you can have full functionality and use of the matrix without Home Assistant or any third-party systems. Before getting into the build details, let's take a little closer look at some of the key features. First, for this video, I'll be showing the system outside or without the final frame enclosure and the acrylic front. This makes things a bit easier to film so I don't get any reflection off the acrylic, but it's primarily because of the extremely cold weather and an unheated garage has prevented me from going out and actually building the frame yet. But it's very similar to my earlier version, and I'll briefly cover it a little later in the video. And of course, the related blog article will have full details and dimensions for my frame build. Now, the matrix has 4 standard display modes: time and temperature, countdown, scoreboard, and text display. Now, the default is time and temperature unless you change the settings. Now, note that nearly everything I show here is customizable, including the LED colors, time zone, whether you want the time in 12 or 24 hours, temperature in Celsius and Fahrenheit, and more. You can opt to show inside temperature only, outdoor temperature only, or both, and specify a lot of other default settings. Now, most of these items you will only specify the values once and won't need to change them again. There are also a number of controller commands down here, including the ability to upgrade the firmware wirelessly over the air. There is one other feature I want to show here, that when the display is in time and temperature or clock mode, the time can be shown in binary clock format. Binary clocks were popular a number of years ago, and of course I have one, where the hours, minutes, and seconds are displayed in a series of blocks or dots representing 1, 2, 4, and 8. A simple checkbox here on the settings will allow you to toggle back and forth between binary and standard clock mode. Next is the countdown timer mode. Now, this can be set anywhere from 1 second up to 99 minutes and 59 seconds, and acts just like you would expect. The countdown can be started, it can be paused or stopped, reset, and when time on the clock does expire, a buzzer will automatically sound. Now, don't worry, that buzzer is configurable and you can turn it off if desired. Next up is the scoreboard mode, and this is pretty self-explanatory, but you do have the ability, for example, to do things like change the team names displayed on the top. And naturally, you can do things like increase, decrease the scores, or actually reset the scores. And finally is text display mode. Now, this allows you to display up to 2 different rows of text, and it does have a number of different text display effects that you can apply, and you can also adjust the speed of each of those as well. So it gives you a little bit of flexibility in terms of displaying text or text messages on the matrix. So that's quite a few features. But wait, there's even more. With a simple click of a button, the matrix turns into a full WLED display with the ability to do all the things you can do with WLED. Note that there is also a microphone on board, so you have the ability to use all of the sound reactive effects as well. And all you have to do is simply turn WLED off, and the system will return back to the standard clock mode. So you get all of the features of the matrix clock itself, plus all of the features of WLED in one matrix build. Well, let's move on by looking how to actually build the system. Now, in the interest of time and because there is so much to cover, I'm going to do this at a little higher level than in some of my other videos. But be sure to check the video description because down there you'll find a link to a written guide that will have complete step-by-step details, parts list, copies of wiring diagrams, and more. In addition, the link to GitHub repo will have a full wiki which will include information on how to install, configure, and use the firmware and the web app. And it also includes examples of how to integrate this into Home Assistant if that's something you want to do. But first, let's take a look at some of the primary parts used. Again, I'm only showing and covering the primary parts used here. Some of the parts are optional and others can be substituted. The written guide provides a complete parts list of everything I used and details those parts that are optional and those that can be substituted. Now for the matrix itself, I'm using 4 1-meter strips of WS2812b LED strips with 100 LEDs per meter. Now using 100 LEDs per meter is what allows the overall build to be around 35% smaller, but also makes installation of the LED strips significantly easier. I'll talk about that more in a bit. Now the primary controller is using a standard 30-pin ESP32 Node MCU style board. This will be placed on female pin headers for easy removal, reflashing, or even replacement. Now you can certainly use other ESP32 boards, but you may need to alter the wiring from what I show here. Now the controller will use a logic level shifter for the LED data line. There are multiple types of shifting methods, and I've covered those in more detail than I care to admit in other videos. But a shifter may be more important here if using dual controllers, as the LED data signal will need to pass through a relay, which can introduce a little additional resistance. Now the type of shifter used is up to you, and the written guide shows wiring diagrams for both types of shifters that I show here. The primary controller also uses 3 normally open push buttons, a rotary encoder, an AHT20 temperature and humidity sensor for the indoor temperature display, and a 5-volt buzzer for the countdown timer. Second optional controller for WLED is similar. Again, I'm using an ESP32, but this time an ESP32 Mini. Again, you can use any ESP32 supported by WLED, just adapt the wiring and the pin headers for whatever ESP32 you're using. I'm adding an IN-MP441 digital I2S microphone for WLED audio reactivity, and of course, again, some sort of logic level shifter. You will need an appropriately sized power supply. Now, the actual size of the power supply is somewhat dependent upon your use case, installation location, and other personal preferences. The written guide goes into significantly more detail, but you need a power supply capable of producing at least 5 amps. You simply cannot power this system with something like a USB cell phone charger, as they cannot supply adequate current to power the 400 LEDs. I'm using a 15 amp power supply, which will provide more than enough LED brightness for my use case. Now naturally you'll need wire, various connectors like DuPont, JST, Wago, etc. And I always recommend a breadboard test before creating any sort of permanent soldered version, so you'll need a breadboard and various jumpers. All this is detailed in that written guide. If you see it here in the video, then the part I use is listed in the blog. This would include additional things like the lumber and the acrylic for the front panel and other parts you need to also build the frame. For the actual build, let's begin by looking at the LED matrix. I actually covered the step-by-step process of creating this exact matrix in a video that's really a precursor to this one. Now, that video, once again linked to down in the video description, shows the step-by-step details, so I won't cover all that again here, but just hit a few of the highlights. If you do refer to that other video, only use it for the matrix build itself and not the controller or the wiring. Even though that project is very similar to this one, there are some key differences. Now, I mentioned that I'm using 100 LEDs per meter for this build as opposed to the more common 60 LEDs per meter, which is what I used in my original matrix build. Now, these denser strips not only allow the same number of LEDs to be laid out in approximately 40% less space, but the distance between the LEDs makes installing the strips much easier. For your matrix to look right and display letters and numbers without distortion, the LEDs must be aligned equally, both horizontally and vertically. With 60 LEDs per meter, the LEDs are spaced 17 millimeters apart, but the strips themselves are only 10 millimeters. This means to maintain equal spacing both horizontally and vertically between each LED, a gap is required between the strips for proper vertical spacing. When using 100 LEDs per meter, the LED spacing is 10 millimeters, the exact same as the strip width. That means that no gap needs to be present between the LED strips, As long as the first strip is level and centered, each additional strip can just be butted up against the prior strip. Now you can use 60 LEDs per meter if you prefer, but the overall size will be larger, and you'll need to assure the vertical spacing between strips is consistent, even, and the same as the horizontal spacing. Regardless of the LEDs used, the layout must be 16 rows of 25 LEDs each. In the event you've not worked with addressable LED strips before, note that the data for the LEDs only flows in one direction. This is always indicated by a small arrow on the LED strip itself. It's important to note this when installing your strips, as the data flow will be in a serpentine fashion, back and forth, starting down here in the lower left-hand corner and ending up here in the upper left-hand corner where power injection wires will be attached. You'll need some sort of solid backer board on which the LEDs will be installed. I used a 1/4-inch thick piece of craft plywood cut to the appropriate size for my planned frame. Now, I applied a coat of flat black paint to the backer board. This isn't quite as critical with 100 LEDs per meter as it is with 60 LEDs per meter, since there would be a visible gap between the strips. Now, to ensure the LED strips don't eventually come loose, I choose to lay down a strip of double-sided tape under each strip. Once the LEDs are installed, you simply wire the strips together. And while the data line will always be in the center, since these strips are flipped back and forth, note that the positive 5-volt and ground connections are flipped on each end, as indicated by my wire colors here. Again, the start of the strip will have a standard 3-pin JST connector, and 2 wires are connected to the end for eventual power injection. Once you have everything wired, I do recommend at this point that you test the matrix if at all possible. Of course, you need some sort of controller for that. If you don't already have one, but you do have the parts for this project, then you can use those parts to quickly throw together a WLED controller in about 15 minutes on a breadboard without any soldering, and I cover that process in another video as well. This will allow you to test the matrix and ensure all of the strips are oriented and wired properly. Just remember to specify the GPIO pin used for the LED data line and to change the total number of LEDs to 400 in the WLED settings. In fact, if you plan on adding the secondary optional WLED controller to your project, you can go ahead and configure this ESP32 for that purpose. Full information on the configuration settings for WLED when used in this project can be found in the GitHub wiki, which once again is linked to down below. Once the matrix is built and tested, you can set it aside for now. Now let's see how the primary controller is put together. Here is the overall wiring diagram for the primary clock controller. Of course, if you're using a different ESP32, your GPIO pin layout may be different. Just make your connections to the same GPIO pins on your ESP32. Now, you can use different GPIO pins, but that will require that you modify the source code and compile your own firmware version. A little bit about that in a few minutes. Now, here is a nearly completed controller. But before I get into that, I always recommend a breadboard test before creating any sort of soldered controller. A breadboard version allows you not only to test and verify your connections, but also allows the components to be tested. Unfortunately, with some of these low-cost, mass-produced electronic components, it's not unusual to receive a dead or faulty component or two. You do want to discover this before you solder that faulty component in place, and then discover it after the whole controller has been built. Of course, to test the system, you also need the firmware installed and configured on the ESP32. I'll cover the highlights of this process shortly, but the GitHub wiki has full information on installing, onboarding, and configuring the firmware onto the ESP32. Once you've fully tested the breadboard components, including any external components, such as the rotary encoder and push buttons, you're ready to move that circuit board onto the more permanent soldered electro cookie version. Now, as I mentioned when discussing parts, the ESP32 will be installed on female pin headers. For one, this allows the ESP32 to be removed. While updates to the firmware are possible wirelessly after the initial install, if something goes wrong, you need to reflash the controller via USB or even replace the ESP32 for some reason, it can easily be removed and replaced without desoldering or disconnecting any other components. The other reason for the pin headers is that a standard ESP32 is just slightly too wide to mount on a breadboard or one of these electro cookie boards and allow through holes on both sides for connecting to your GPIO pins. By using the header, it raises up the ESP32, allowing wires to be connected to the through holes underneath the ESP32. In addition, since I'll be mounting this electro cookie board on either offsets or in an enclosure with built-in offsets, it allows me to run wiring on the top of the board and solder underneath, or I can run wiring on the bottom side of the board and solder from the top. Initially, as shown here, all wiring for the external connections at this point are just bare leads, about 12 inches each. Now, these will eventually be cut back to length and connectors added once the controller is mounted on the back of the LED backer plate and is in the frame. This allows the wiring to be run through holes in the frame like for the control box before the connectors are added. How you route the wires and the order of installation is somewhat up to you, but I cover the process in that written guide. In a nutshell, I generally start by installing the headers, then the shifter, then I will complete any point-to-point onboard wiring before completing all of the wiring for external connections. But again, the actual process and the order of making all of these wiring runs is totally up to you. So while the Matrix can be fully configured and controlled via the web app, sometimes it's hard to beat the convenience of physical controls. So my build includes a small control box that can be mounted on or near the frame. The control box houses a rotary encoder, 3 push buttons, and also has the temperature and humidity sensor for the indoor temperature reading. Now I've placed this in a 3D printed enclosure, and you'll notice a couple of other 3D printed parts, but none of those are required for building this clock. You can use something like a small project box, or you can even mount these controls directly to the frame if you don't have access to a 3D printer. As you can see here, where I've attached an older version of the control box directly to the frame, there's nothing saying it has to be attached to the frame. In the case of the one I installed in the garage, where the Matrix is quite a bit higher, where it would have been hard to reach that control box, I simply mounted the control box down below the actual Matrix itself. So you can put the control box pretty much anywhere you want. But the wiring for this is actually pretty simple. Gently pull this apart, and you can see that the rotary encoder actually passes through the lid, and our temperature sensors installed down there in the bottom, and then there are the 3 buttons. All of the wires just run straight out through this braided sleeve cable that will eventually feed into a hole in the side of the frame. Rotary encoder can be used to control the brightness of the Matrix display, and this works both in standard clock mode with the primary controller and in WLED mode as well. When on the primary or the clock display mode, then the push buttons can be used to toggle through the different display modes of the primary controller, or if something like countdown mode, you can start, stop, and reset the time. When in scoreboard mode, you can control both scores, or you can simply reset the scores as well. When in WLED mode, these buttons can be used to cycle through the various presets that you have defined in WLED. When in WLED mode, a click of the rotary encoder will simply turn WLED off and return the clock back to the normal primary controller. As mentioned earlier, you can add an optional secondary controller to give you full WLED along with all of its effects and features. If you do install the secondary controller, a relay will be used to automatically switch the output between the 2 controllers and the LED matrix itself. Now, if you don't want to include this optional secondary controller, you can simply omit it. But if you do want to include it, let's take a look at the build details and use of the relay for that. This is pretty much just a standard WLED controller, which I've shown in numerous other projects. For this particular controller, I'm opting to use an ESP32 Mini. No particular reason other than to show that you can use different types of ESP32s. Any ESP32 that is listed as compatible with WLED per its website can be used here. Again, adjust the wiring diagram to use the same GPIO pins for your ESP32 if they're laid out differently than mine. Once again, the ESP32 is mounted on female pin headers, allowing connections to be made underneath the board itself. And you may have noticed that there are 2 data lines here running to the logic level shifter instead of the normal one. No, I'm not using multiple LED data pins. One is the standard LED data line, but the other is a signal line for the relay that will switch the data going to the LEDs between the 2 controllers. I'm using a 5-volt relay, which not only means that it needs 5 volts for the relay's power, but it expects a 5-volt control signal. And as you're likely aware if you've watched any of my other videos, the GPIO pins on the ESP only output 3.3 volts. And like the LEDs themselves, you can sometimes get lucky and be able to trigger a 5-volt relay with the 3.3 volt signal. But it also may not work, or it may be intermittent. Since we already have the shifter in place for the LED data line, a second channel can simply be used to also shift the relay signal. Now note that even if using something like the SN74AHCT type shifter, it also has 4 channels, so the same process can be used. Now alternatively, you could use something like a 3-volt relay, in which case the signal from the GPIO pin can be used directly. But this relay also needs 3 volts for its power, so you'd have to add something like a buck converter to step down the 5 volt from the power supply down to 3 volts for the relay. Using a 5 volt relay and a shifter, especially if already using one for the LED data line, results in fewer components and less wiring. Again, you can connect this controller to your LED matrix if you already have it built to test it and to assure everything is working properly. Of course, you'll need to install WLED onto the ESP32 if you haven't done that yet. The only other major difference here is I do have all the wiring for the INMP441 microphone already installed here, and like the other wiring, this will eventually be cut to the length and connectors will be added. Now, as mentioned, due to the extremely cold weather, I've not been able to actually get out and build the frame yet, but I'm going to use the same technique that I did in my prior Matrix build. It's just the dimensions will be slightly different. And again, you can find those dimensions in the written blog article linked to down in the video description. These photos are from my original 60 LED per meter matrix, as you can tell due to the gap between the LED strips. So while the dimensions will be different, the process will be the same. I'll show the planned dimensions for the 100 LED per meter version, but you can also find these and more details about building the frame in the written guide. Now originally I used 1x4 pine boards for the size of the frame, but since I'm relocating the power supply for this build, I don't need quite this much depth, so for this version I'll be using 1x3 pine. And the first step is to route the grooves for the LED backer board and the front acrylic panel. Now the grooves for the acrylic need to be rounded on all 4 sides, but the groove for the backer board only needs to be on the top and bottom parts of the frame. Why is that? Well, the backer board is actually narrower than the frame. This allows for wirings for the LEDs to wrap from the front to the back. You won't see this gap when it's finished. Once the frame sides are routed and cut to size, you can determine the final dimensions and cut the acrylic for the front. Now the acrylic should be about a ½ inch wider in both directions than the inside dimensions of the frame, so that the acrylic panel will slide into and be held in place by the grooves that are routed in the frame. Now this next step is optional, but I like to apply just a couple of light coats of frosted glass spray paint to both sides of the acrylic. You don't want to apply too many coats and cause the LEDs to look fuzzy or out of focus, but a couple coats of frosted glass paint will just slightly soften the harsh glow from the LEDs. If you already have your LED panel and controller built, you can power them up and try holding the acrylic sheet approximately a ½ inch in front of the LEDs to test, and then apply additional coats until you get the look you want. Or you can skip this step altogether and just use untreated acrylic. With everything cut to size, paint or apply any desired finish to the frame, or leave it natural if that's what you prefer. Obviously, if you're going to paint the LED backer board, that needs to be done before the LEDs are installed. Now simply assemble the frame, inserting the completed LED backer board and acrylic front panel into the grooves on the frame. You just want to make sure that that LED backer board is precisely centered in the frame, since there are gaps on both sides. Now I'm using simple butt joints since the final project will be trimmed out, but you can miter the corners here if desired. But I am going to make a correction to my original build where I countersunk, puttied over, and painted all the screws in the frame. But that will be a problem someday if an LED or LED strip fails. I can't access the LEDs in my original build without also destroying the frame. So for this version, I'll go ahead and glue and countersink the screws attaching the bottom and the 2 sides. But for the top, I'll use a combination of inside angle brackets and a couple of exposed screws. This way, if necessary, I can remove the top from the frame and slide the LED backer board out should I need to replace an LED strip. In addition, I can slide the acrylic out and replace it as well should it become damaged or cracked. Finally, 2-inch trim is installed around the frame. If your dimensions are correct, this should perfectly frame the LEDs, covering the gaps around the edges without covering any of the LEDs. Again, you can take my idea, or you can come up with your own idea for to build a frame or an enclosure for the Matrix and controllers. So now let's move on to installing all the components and making all the wiring connections. In my build, all components except for the power supply will be installed on the back side of the LED panel or on the frame, after I'm able to actually complete the frame. In my original build, the power supply was also on the back panel, but this made the display much heavier for things like mounting on the wall. Plus, with the new build being approximately 35% smaller, squeezing everything in would be a challenge, so I opted to move the power supply outside of the main frame for this build. Now, the size of the power supply you select will be based somewhat on the intended use. Both controllers have brightness limiters that can be used to limit the current pulled by the LEDs, and you should ensure these are set for the power supply used. The written guide and the GitHub wiki both contain information on selecting the proper power supply size and how to configure the limiters in the controller's firmware. How you lay out your components on the back of the Matrix is somewhat arbitrary, but you will want to determine the location of any components that will be installed outside of the frame, like the control box, microphone, and buzzer if used. This is because you need to attach these components, then drill holes in the frame to pass the wiring through so they can be connected to the other components. Now note this also includes the main power line coming in from your power supply. The components inside of the frame can be mounted in a number of different ways, and I'm showing a couple of different options here. I'm using simple brass PCB offsets for my primary controller and for the relay, but for my secondary WLED controller, I actually have it in a 3D printed enclosure that is attached to the backer board. Use any method you like, but be extremely careful that any screws or other mounting options do not travel and penetrate through the backer board, potentially damaging or coming in contact with the LED strips on the front. If necessary, use washers or 3D printed spacers like I did for the relay mounts here. Now, by the way, I did mention earlier that the 3D printed parts are not required, but if you do have access to a 3D printer, you can find the design files for all my 3D printed parts in the GitHub repo. Once all the components are mounted and all the necessary wiring has been routed to the back side of the frame, you just need to connect the appropriate leads together. Of course, you can solder these wires together, but I like all my connections to be detachable should I need to upgrade or replace a component down the road. Now you can use Wago connectors, spade connectors, or even wire nuts if desired. Personally, I like to use JST connectors because they are keyed and only connect in one way. Between using different numbers of pins and alternating the male-female connector orientations, I can create connections that assure the proper component is always connected to the proper wiring leads. In addition, since these JST connectors are keyed, it will prevent me from actually flipping them over and connecting them backwards, possibly reversing the polarity of a component and frying it. I also assure I'm using the same color wiring on both sides of the connection, and here I added a little colored tape as well, just for an additional visual check, but that's certainly not necessary. For components that have pin headers like the rotary encoder, temperature sensor, or maybe the microphone for WLED, I make custom cables that have a DuPont connector on one end for connecting to the component's pins and a JST connector on the other end for connecting to the wiring from the controller. Again, how you opt to run and connect the actual wiring is up to you. You can certainly use something like spade connectors or these Wago clips or even wire nuts, or you could actually solder the wires directly together. But I do want to mention one more thing about power and powering runs. Now I'm opting to use a couple of terminal blocks to distribute the 5-volt power to the two controllers, the relay, and the LEDs themselves. Note that you need to run the 5-volt power for the LED strips in parallel to the controllers. Do not try to route the 5-volt power through either controller board and then to the LEDs, as they're not rated for the current draw required. But this does bring up an important safety issue. Assure that all wiring, connectors, and components used are rated for the expected current draw of the system. In my case, I'm using a 15 amp power supply, but will be limiting the LED current to a maximum of 10 amps via both controllers' option settings. So in my case, all wiring and connections related to the LEDs must be rated for at least 10 amps or more. Now, I state the wire gauge I used in the written guide, but your project may be different based on the power supply used. I can't necessarily tell you what gauge wire to use, but there are online calculators and charts regarding wire size and amps, so you can utilize those to determine the proper wire size to use. If you are using higher amps, you may then also want to consider adding a fuse to the primary 5-volt line from the power supply. I won't cover that here, but I do talk about it in a few of my other LED-related videos. Unfortunately, the weather's prevented me from completing the frame and therefore all the final wiring. But when I do get it done, I'll post final photos in the written guide. Now let's take a quick look at the firmware, the web app, and then the API and how it can be used to integrate this into Home Assistant for use in your automations. Very first time, you must flash the firmware via USB cable. After the initial flash, all future updates can be done wirelessly over the air, but you'll need a couple of things before you can initially flash the firmware. First is the actual firmware itself. Go to the GitHub repository, locate the latest release, and from the assets, download the bin or the binary file and save it locally. You do not need the zip files unless you want a full copy of the entire repository, including the source code. Now you'll also need a flashing utility. There are a number of free utilities out there, including things like Node MCU Pi Flasher, ESP Tool, etc. I'm using ESP Home Flasher. No, you don't need ESP Home to use the flasher. And again, links for these can be found down in the video description and the written guide. So launch your flashing software and connect your ESP32 to an available USB port on the local machine using a micro USB data cable. Now, the options shown here may be slightly different depending on the flashing software being used, but you'll generally select the COM port that your ESP32 is connected to, browse to and select that bin file that you downloaded. Then you simply hit the flash button to begin. And it'll go through and begin the flash. And if you do run into any sort of issues with the flashing, check out the written guide or the GitHub wiki that has information on common issues and solutions related to flashing the firmware. And once the flash is complete, you can power cycle the board to reboot it, or if you want, you can go ahead and install the ESP32 into the completed controller at this point. If you do install the ESP32 into the controller and the controller is connected to the LEDs, when you power on the system, the display will show Join Wi-Fi, meaning the system has not yet been onboarded and joined to Wi-Fi yet. At this point, the board should be broadcasting a local hotspot called Matrix Clock AP. Grab your phone or other mobile device and join this local hotspot. You may be warned about no internet connection, but that's fine. Maintain the connection if prompted. Now open up a browser on your mobile device connected to the hotspot and navigate to the onboarding page. This allows you to enter your local Wi-Fi information and a device name. The device name is used as the Wi-Fi host name, the Arduino OTA name. It can also help identify which matrix you are accessing if you have more than one matrix installed on your network like I do. So make sure each device name is unique if you have more than one. Finally, specify the milliamp limiter, which I've talked about a few times already. Note that both controllers specify their limiters in milliamps, so ensure you're entering milliamps and not amps into this field. Once all values are entered, hit the submit button, and the controller will reboot and attempt to join your Wi-Fi. If successful, the display will blank and then briefly display the last two octets of the newly assigned IP address. Now, my network begins with 192.168, so from this output, I know the IP address for my controller is 192.168.1.182. Of course, you can also use your router to find the IP address if necessary. If you still see a join Wi-Fi message here, then the controller was unable to join your Wi-Fi. Look again with your mobile device and you still see the Matrix Clock AP hotspot. This hotspot will only broadcast when Wi-Fi cannot be joined. Try the onboarding process again, ensuring your Wi-Fi and password are exactly correct. Both fields are case sensitive. If the controller does join your Wi-Fi, after the IP address, you'll see a short upload message. Now, this doesn't indicate that anything is uploading or that you need to upload something. It just indicates that over-the-air updates are now enabled and the message is only displayed for a couple of seconds. After that, the controller will go into normal display mode, showing the time and temperature by default. Now, don't panic if the initial time or temperatures are incorrect here. You still need to complete some initial configuration steps, such as entering your time zone and API key for the external temperature. All this is done via the web application, which is reached by simply entering the IP address of the controller into a browser of a device on the same Wi-Fi network. I showed a bit of the web app towards the start of this video, and of course the GitHub wiki has full instructions on what each option or field does, so I'm not going to cover all those here. But suffice it to say that the system is very configurable via the settings and options. I do want to point out a couple of things you'll want to review and set up upon initial configuration. The first is your time zone settings, and if you want the time to periodically sync to an NTP or time server. Now note that if you have a local NTP server on your network, you can use that instead of an external source. You can also manually specify the GMT offsets instead of a time zone. You can even manually specify the time if desired, but do note that if you're not syncing the time and manually setting it, you'll need to reset the time whenever power is lost to the controller. The other setting here is for the outdoor or external temperature. The firmware uses the free Open Weather Map service and your latitude and longitude to get the current outdoor temperature. Now, this does require that you obtain a free API key, and the GitHub wiki covers the process on how to do this. If you don't want to obtain a key or don't really care about outdoor temperature, you can leave this blank and simply toggle the option to only show indoor temperature. I'm also working on an upgrade to the firmware where the outdoor temperature can be pushed to the controller from another system like Home Assistant. Hopefully that update will be ready before you build your own version. If you opt not to use Open Weather Map and either sync the time locally or opt not to sync the time, then the controller doesn't even need internet connectivity. The controller only connects to the internet for time syncing and to pull the current outdoor temperature. If not using those, then you can actually block the system from using the internet. Now note that although internet might not be required, Wi-Fi still is, so that you can access the settings. Now, while the web app is the primary method of configuring and controlling the matrix, it's not the only way. As opposed to MQTT in the initial version that required an MQTT broker, this version provides an API, and this API can be used to integrate and control the system via an external system like Home Assistant. Here I've used that API to create a simple sample dashboard here in Home Assistant. And note that I'm able to recreate most of the web app options using this API. So for example, just like before, I can actually change modes, and notice as I'm changing modes, I'm getting different controls down here for doing things like, increasing or resetting the scores. And of course, I have all those different modes available. So not only can I create a dashboard here, but now that I've got these entities defined in Home Assistant, I can actually use it in automations. So for example, maybe when I turn the lights off at night, it also turns the LEDs off on the clock. And of course, there are a lot of other possibilities as well. You can find the sample YAML that I used to create all of these entities and to create this dashboard, along with information on the API in the GitHub repo. So while quite a bit of soldering is involved here, it's all pretty basic, and if you're somewhat new to soldering, this is a great project to hone your skills. No programming or code is required, but the full source code is available if you want to tinker around or make modifications to the firmware for your own use. Next, I'd like to take some of the improvements I did in this project and apply them to some of my older projects, like maybe the parking assistant or the DIY amp project. But this means that my video release schedule might be a little bit spotty moving forward for a while because nobody wants to sit and just watch a video of me writing code. But I will be back soon with more videos on Home Assistant and DIY electronics. Until that time, I'd like to say thank you for watching, and I hope to see you again soon.